So let's talk about one of the most challenging but important concepts in thermodynamics, entropy. To come to our definition of entropy, we need to start with the Clausius inequality. If you're at all unsure about the Clausius inequality, make sure you go back and revise that first, because it's going to be absolutely integral to our understanding of this new state property that we're going to define, entropy. The Clausius inequality is made up of two parts. Firstly, an equality part, which says that for a reversible cycle in a heat engine or a heat pump, the cyclic integral of the heat transfer divided by the temperature of the working fluid to which the heat transfer is taking place is equal to 0. The other part of the Clausius inequality, the part that gives it its name, says that the cyclic integral of the heat transfer divided by the temperature of the working fluid for any irreversible heat engine or heat pump cycle must be less than 0. We combine these two statements together and we get the general statement of the Clausius inequality, that for all possible cycles, the cyclic integral of the heat transfer divided by the temperature of the working fluid must be less than or equal to 0. We're going to make use of both the equality and the inequality parts of the Clausius inequality, but first we're just going to focus on the equality, the one that's true for totally reversible cycles. And so remember, a totally reversible cycle is a cycle that is made up entirely of totally reversible processes. And if that's true, then the cyclic integral of the heat transfer divided by the temperature of the fluid will be equal to 0. So now let's consider three totally reversible processes: A, B, and C. These are different paths between the thermodynamic states that we've called state 1 and state 2. A is one totally reversible path from 1 to 2, C is some other totally reversible path from 1 to 2, and B is a totally reversible path from 2 back to 1. This means then that since all of these processes are totally reversible, if we follow path A from point 1 to point 2, and then B from 2 back to 1, this is a totally reversible cycle, and likewise if we move along path C and then along path B, that is also a totally reversible cycle. And from the equality in the inequality of Clausius, we can therefore say that for AB or CB, the cyclic integral of the heat transfer divided by the temperature must be equal to 0. So let's firstly consider the reversible cycle AB, and let's evaluate the cyclic integral of the heat transfer divided by the temperature. Remember that a cyclic integral is really just a line integral along a closed path. So when we say the cyclic integral for the cycle AB, what we're saying is evaluate the integral along path A, and then evaluate the integral along path B, and sum them. And so that's exactly what we've done here. And because this is a totally reversible cycle, the sum of the integral of heat transfer divided by temperature along path A plus the integral of the heat transfer divided by the temperature along path B must be equal to 0. So let's put that aside for now, and instead consider the reversible cycle made up of the paths C and B. Once again, because it's a reversible cycle, the equality holds. So we evaluate our cyclic integral again, and we get the sum of the integral along path C, and then the integral along path B, once again is equal to 0 from the equality part of the inequality of Clausius. So now we have these two results from the cyclic integrals for the two cycles we defined, AB and CB. And we're going to call the cyclic integral for AB equation 1, and the cyclic integral for CB equation 2. Then we're just going to subtract equation 2 from equation 1. The right-hand side of both is 0. 0 minus 0 is fairly straightforward. And we'll see that we have this common factor in the integral of the heat transfer divided by the temperature along the path B appears in both. So these terms are just going to cancel out, and all that will be left is the statement that the integral of the heat transfer divided by the temperature along path A is equal to the integral of the heat transfer divided by the temperature along path C. Now this is a profoundly important result, because remember, we actually haven't said anything about paths A and C except that they're reversible. So this statement is true for any reversible path A or C, not just the ones we've drawn here. We can make it look like any path we like as long as we satisfy the reversibility condition. The integral of the heat transfer divided by the temperature will be the same. It's independent of the path. And something that is independent of the path is a point function. It is defined uniquely at a given point in our thermodynamic variable space, just like pressure or temperature or density or specific volume or any other property you want to name. So therefore, this is also a thermodynamic state property. The heat transfer divided by the temperature of the working fluid for an internally reversible process is a thermodynamic state property. And given the title of this video, it should come as no surprise to you that the name that we've given that state property is entropy. Entropy is defined by the heat transfer divided by the temperature of the working fluid for a reversible process. Now, this really only gives us a definition for the change in entropy. If we want to define absolute values of entropy, we need to bring in the third law of thermodynamics, but really just talking about changes in entropy is already a very powerful tool. And we can calculate the change in entropy along a reversible path simply by evaluating this integral. Now, of course, we would notice that this definition requires reversibility. And this is a pretty significant constraint when we consider that there's actually no such thing as a reversible process. So how is this useful to us? Well, firstly, let's clarify what kind of reversibility we're talking about. Our definition for entropy came from considering reversible cycles. And reversible cycles are cycles made up of totally reversible processes. So our original definition requires total reversibility. However, think about what the S means here. When we're talking about a thermodynamic variable, whether it be entropy or pressure or temperature, we're only talking about that property inside our thermodynamic system. And if we're only talking about what's happening inside the system, there's no difference between totally reversible and internally reversible. Inside the system, it doesn't care if there's irreversibility outside the system boundaries, only if it's inside the system boundaries. So we can still evaluate a change in entropy by looking at the heat transfer divided by the temperature just for an internally reversible process. That's quite a tricky concept, so let's explore it a little bit further. Let's consider a pair of processes here. They're both going to be isobaric expansion processes. They're going to be quasi-equilibrium. There's going to be heat transfer in both cases, and in the case at the top, it's happening through a large temperature difference, and at the case of the bottom, it's happening through an infinitesimal temperature difference. So we have our isobaric expansion. It's happened in a quasi-equilibrium manner. The system's gone through a series of equilibrium states. The system does not care whether its thermal reservoir was at 2000 degrees or 300 degrees. It just knows that it received some heat input and work was done on the universe, and it passed through a series of equilibrium states from 1 to 2. The same equilibrium states in both the case at the top and the case at the bottom. The final state of the system, which includes the entropy at state 2, does not depend on the temperature of the external source. Thus, the change in the entropy can be evaluated simply from the magnitude of the heat transfer divided by the temperature at which it took place, as long as there were no irreversibilities within the system boundary. So again, to emphasize, both processes here will result in the same change in entropy inside the system. And when we write out an expression like ds is delta Q on T, our S here refers to the entropy inside the system. Just like our PV diagram here, the P that we're referring to is the pressure inside the boundary of the system, not the pressure outside the boundary. Now, what about outside the system boundary? Well, the process at the top will have irreversibility associated with it because we have heat transfer through a large temperature gradient. So entropy will be generated in the universe in the process at the top and not in the process in the bottom. But as far as the thermodynamic state of the system, the control mass that we're presumably analyzing here, it doesn't care about that. It's only concerned if the amount of entropy inside the system has changed, and in each case it will have changed by the same amount. So we used the equality part of the inequality of Clausius to come up with our definition for entropy. But now we're going to use the inequality part to say something quite profound about entropy. So let's consider our two little processes A and B once again. And just like we did before, we're going to assume that B is totally reversible. But now we're going to relax a bit about A and we're going to say it can be whatever it likes. Maybe it's reversible, maybe it's not. And then that means we now need the full inequality of Clausius because we don't know if A is reversible or not yet. So the cyclic integral of the heat transfer divided by the temperature might be equal to 0 if it is reversible, or it might be less than 0 if it's not. So we can expand that cyclic integral out and say that it's equal to the integral along path A plus the integral along path B, which we know is a reversible path. Now once we've expanded it like this, we can say, doesn't that second term look like something we were just discussing? And of course, that's where we get our definition for the change in the entropy of a system from. So we can substitute this into the expansion of our cyclic integral and replace the integral along that reversible path with the change in the entropy of the system. Now we can't do this for our integral along path A because we haven't said whether or not it's reversible, and we can only use that definition of entropy along a reversible path. So if we take this expression now, we can rearrange it and say that the change in the entropy must be greater than or equal to the integral evaluated along that path. Of course, if it's a reversible path, it will be equal to it, and we're simply back to our definition for entropy. But it's when it's not equal to it that it gets interesting here, because that means the change in entropy must be greater than the result of evaluating that integral. So the change in the entropy will always be greater than or equal to the heat transfer divided by the temperature. What does that mean? Well, let's consider two processes between points 1 and 2 here. We're going to assume that A is internally reversible, and that means that the change in entropy for path A will simply be equal to the integral of the heat transfer divided by the temperature. But if B is not internally reversible, what we can say is that the change in entropy will be equal to evaluating that integral, but we know that the change in entropy must be more than that. So there's additionally an entropy generation term. So the integral of dq on t you can think of as an entropy transport term. That's entropy crossing the system boundaries as heat transfer happens. But our generation term is different. That's a production term. That's entropy being produced inside the system due to internal irreversibility. So it is irreversibility that produces entropy. And if our process is not internally reversible, that means there's irreversibilities taking place inside the system boundaries, and entropy is being produced inside the system. And it's very important to note, it can be produced, but Sgen can never be negative. So we have a general expression for the change in entropy. It's equal to the amount transported across the boundary through the heat transfer, which we can only evaluate along an internally reversible path, plus some amount generated by irreversibilities taking place inside the system boundary. Things like viscous dissipation or unrestrained expansion. So if Sgen is greater than 0, the process has some internal irreversibility associated with it. And of course, all processes in the real world produce some amount of entropy. In our nice idealized world, we can talk about internally reversible processes where no entropy is generated inside the system boundary. But even in our nice, simple, idealized world, there can never be negative entropy generation, at least not at the sort of scales we deal with in engineering thermodynamics. So the best we can get is no generation for internally reversible processes. We can never have a negative value for entropy generation. So here we've talked about how we define the property of entropy, and how from the inequality of Clausius, which of course comes out of the second law of thermodynamics, we know that entropy will never be destroyed, only created or transferred. This doesn't cover what entropy actually is, but that's a topic for another day. Good luck.